Hello, Y13. Welcome to your chemistry lesson on storage and fuel cell. So it's going to be pretty quick. I think a lot of the information is in your textbook, and I don't have much to add, but I'm going to spend a bit of time on the hydrogen fuel cell at the end. So please make sure you take notes. And at the end, you have to do some summary questions, and I've made a mark scheme for you. So let's begin. Maybe. So there are three different types of batteries you need to know about. All of them are going to involve a redox reaction, okay, all of them. And you just need to know the name of some of them. So the primary cells are non-rechargeable. They are going to provide electrical energy till all the chemicals have reacted. The voltage is going to fall over time, and then the cell is going to be flat, and then you're going to have to be thrown away, okay? So all the round little batteries you have in watches, for example, are primary cells. All the non-rechargeable batteries that you're using for, I don't know, a remote control. There's quite a lot of objects, but you guys are too young to actually use them. But like pretty much all these batteries, non-rechargeables, are primary cells. They're going to run out over time, go flat, and will have to go to the bin, which is not particularly environmental friendly. The second type, the secondary cells, are rechargeable. So the chemicals in a cell are going to react, they're going to provide electrical energy, they're going to provide the EMF or the potential difference. They're going to go flat over time, but if you plug them in, they can be recharged. All the reactants are going to be regenerated, therefore they can be used over and over again. And this is the type of cells that you're going to have in your phones, in your laptops. You can also have the AAA and AA, which are rechargeable. All these are secondary cells. So they're going to involve redox reaction that are reversible when applying an electrical current to them. And the last one are the fuel cells. So these cells are not going to, how can I say that? Like have the chemicals inside. You need to provide the reactant constantly. Okay, so you're going to use a fuel and an oxidant, and they're being consumed. You can't really recharge them, but you're going to supply the reactant to do the reaction. Again, we're going to see that in more details very soon. I was supposed to erase that. So this one was the first batteries that was created, the voltaic pile or pile. Good old Volta. They gave a name to the volts. So he had like two different metals, okay, on top of each other, layers of them, separated by cardboard dipped in a solution containing ions, usually salt, and that managed to generate electricity. Well done. But before I talk about hydrogen fuel cells, about batteries, you don't need to know all the reactions that take place in primary or secondary fuel cells, okay? But you will be given redox systems, and you'll be able to, using the electrode potential, figure out which one is the negative electrode, which one is the positive electrode, and the reaction that is taking place. We'll see in the practice question later that sometimes it's going to be in acidic conditions. So in that case, you're going to use H plus and H2O to balance the number of oxygen. Sometimes you're going to work in alkaline condition. In that case, you're going to use OH minus and H2O to balance your equation. Okay, don't worry too much about it. You'll always be given the redox couple. You may be given the equation. So just make sure that if they tell you it's in alkali condition, you're using OH minus. If you're using acidic condition, you're using H plus. Okay, now the hydrogen fuel cells. Modern fuel cells are based on hydrogen or hydrogen-rich fuels, such as methanol. Okay, so organic compound with a lot of hydrogen. CH3OH, it's 4 hydrogens, very rich in hydrogen. It can be used as a fuel to generate electricity. The definition, you can pause to write this down. A fuel cell uses energy from the reaction of a fuel with oxygen to create a voltage. Okay, it's very similar to combustion, the same reaction as combustion, except you're not generating heat like you usually do for combustion, but you're going to use the energy transferred to generate an electrical current. In a fuel cell, you're going to have your reactant. so your fuel and your oxygen, they're going to flow in continuously, and the products are going to flow out. We'll see that in most of them, the product is going to be H2O. The electrolyte, so the ions themselves, are going to remain in the cell. Sorry, 2 seconds. My daughter is here. Oh, it's a book token. Can we look at it after? Thank you, my love. And these fuel cells do not need to be recharged because they don't need to be plugged in. You just need to replace the fuels continuously. So, two main types of hydrogen fuel cells. In alkaline electrolyte conditions, so OH minus, and in acidic conditions with H plus. Both have the same overall cell reaction. Hydrogen reacts with oxygen to form water. Okay, so you're constantly going to need to provide the hydrogen and the oxygen, and you're constantly going to produce the H2O, which you're going to relieve from your battery or from your cell. So this is the alkali hydrogen fuel cell. So you can see on the left-hand side, hydrogen is going to be introduced there. Oxygen is introduced to the right-hand side. Water is going to be produced on the left and removed. The two redox systems are as follow. So the first one, H2O, 2H2O plus 2 electrons goes to hydrogen plus 2OH minus. The second one, half O2 plus H2O plus 2 electrons goes to 2OH minus aqueous. If you look at the electrode potential, the most negative one is minus 0.83. That means that hydrogen, in that case, will lose electron and be oxidized. Okay, so we're going to switch the direction of the first system, where hydrogen plus, so H2 gas plus 2H minus goes to 2H2O liquid plus 2 electrons. The reduction reaction, half O2 will react with H2O plus 2 electrons to form 2OH minus. Before writing down the overall equation, we make sure we have the same number of electrons involved in both reactions. That is the case. We also have 2OH minus present on both sides, so we can simplify it. And we also have one H2O on the left and 2 H2O on the right, so we can simplify it as well. So the overall reaction, H2 plus half O2 goes to H2O. And the potential difference you're going to measure, if you're using 1 mole per dm cube of all the ions and a pressure of 100 kilopascal, is going to be 1.23 volts. Okay, you may need to remember those systems. You may need to remember which system to use if you're given a list of redox systems. Okay, so if you work in alkali conditions, make sure you involve OH minus ions. For the acid hydrogen fuel cell, so again, very similar. The hydrogen is going to be introduced on the left-hand side, the oxygen on the right-hand side, and this time the water is going to be removed from the right-hand side. The water is going to be produced at the cathode, where the reduction takes place. So the two redox systems, 2H plus 2 electrons goes to H2, and half O2 plus 2H plus 2 electrons goes to H2O liquid. So again, we look at the electrode potential values. The first redox system is the most negative or the least positive. So it has to be switched. That's going to be the negative electrode. And we have to switch the direction. So the oxidation reaction, H2 goes to 2H plus 2 electrons. Okay. The reduction reaction is the second redox system without switching position. So it's going to be a gain of electron, where half O2 react with 2H plus and 2 electrons to form H2O liquid. Before writing down your overall equation, we need to make sure we have the same number of electrons involved on both sides. That is the case. And we end up with an overall reaction, H2 plus half O2 gas plus H2O liquid, which is exactly the same overall reaction as for the alkali fuel cell. Okay. And again, the potential difference will be exactly the same. We're going to do the electrode potential of the positive electrode plus 1.23 minus the electrode potential of the negative electrode 0, which is plus 1.23 volts. Molto facile. Take a bit of time. Don't panic too much. You don't need to know them by heart. Just make sure that if you're working in acidic conditions, you're involving the hydrogen plus ions. If you're working in alkaline condition, make sure you're involving the OH minus ions. So at first, the hydrogen fuel cell appears to be very green, very clean, because the only product is water. So using it is not going to generate any pollution. Problem is the production of hydrogen. Most of the hydrogen that is made from crude oil, or is going to require energy, which requires the combustion of crude oil. So it's not that green to produce. Okay, it's green to use it, not green to produce it. So the challenge for the next generation of chemists will be to produce hydrogen pretty much cleanly. So the other problem with the hydrogen fuel cell is that if you have you need a constant supply of hydrogen. Okay, the oxygen is mostly present in the air, but you need to carry hydrogen, which is slightly explosive. Remember the squeaky pop? Yeah, you don't really want the squeaky pop to happen in your car. So there is pros. Okay, using the hydrogen fuel cell does not generate carbon dioxide pollution, but you need to consider the storing, the transporting of the flammable gas, as well as the production of hydrogen. So overall, the non-rechargeable cells are good because they're cheap. Problem is they can only be used once, and then they go into wasteland, so that's wasting a lot of chemicals, and that's a lot of pollution. The rechargeable cells are pretty beneficial as well because they're relatively cheap, but they can be recharged, which means that, for example, if you attached a rechargeable cell to a solar panel, you can store electricity, which is a very hard thing to do. So you can store electricity and use later when needed. The fuel cells, again, only water vapor is produced when using it, which is good. Reduce the pollution. The problem is keeping it, transporting the hydrogen and producing the hydrogen, which can generate pollution. Okay, now I'd like you to keep that, answer the summary questions. Okay, pause the video and we'll mark it when you're done. Okay, I really hope you did pause the video and try to do the activity by yourself, but let's go through the mark scheme together. So the key difference between the primary cell and the secondary cell, the primary cell cannot be recharged, but the secondary cell can. Key characteristic of a fuel cell, the fuel cell uses energy from the reaction of a fuel and oxygen to create a voltage or electromotive force or a potential difference. It can be used continuously without needing to be charged as long as the fuel and the oxygen are supplied. Question 3. So again, you're given two redox system here, and we know that the potential difference is 1.3 volts. And we know that CD is the negative electrode. So if CD is the negative electrode, we're going to have to switch the direction of the reaction. Is that going to be an oxidation? So CD plus 2OH minus goes to CdOH2 plus 2 electrons. That's the negative electrode. At the positive electrode, we're going to keep the second redox system unchanged. So 2NiOH plus 2H2O plus 2 electrons goes to 2NiOH2 plus 2H minus. You add on all the reactant and you simplify a little bit and you end up with CD plus 2NiOH plus 2H2O goes to CdOH2 plus 2NiOH2. B. Use oxidation numbers to show the elements that are oxidized and reduced in the working cell. So cadmium at the start goes from 0 to plus 2 in CdOH2. Remember, each OH is minus 1, so CD has to be plus 2. Therefore, cadmium is oxidized. Nickel goes from plus 3 in NiOOH to plus 2 in NiOH2, so it's reduced. So remember, in NiOOH, the oxygen is minus 2, the OH is minus 1, the Ni therefore has to be plus 3. To calculate the potential difference, you're going to do the electrode potential of the positive electrode minus the electrode potential of the negative electrode. We know that the potential difference is 1.3 volts. We know the electrode potential of the negative electrode is minus 0.81. So we end up an electrode potential for the positive electrode, which is the NiOOH, and it's 0.49 volts. Finally, when you write down those two together, you make sure you have the same number of electrons on both sides. That is the case. So you have CD. I made a mistake, Rod, didn't I? I did something silly here. Oh no, construct the overall equation when the cell is being charged. So when it's being charged, you're going to do the reverse reaction to what we found in 3a. Okay, so the products are going to react together.